Water is life, but the same water is increasingly taking life. The monsoon of 2025 ended with 8% above normal rainfall, officially a normal season. Yet across India, we witnessed two contrasting realities: catastrophic floods in north and northwest India and drought-like conditions in eastern parts. These extremes tell us that rainfall totals alone no longer define the monsoon. Hello everyone, I am Hiren Solanki, a PhD scholar from the Water and Climate Lab at IIT Gandhinagar. As we know, climate change is intensifying the frequency, intensity, and variability of rainfall events, bringing more rain in fewer days and longer dry spells in between. Therefore, understanding the changing hydrological cycle is essential if we want to forecast flood or droughts more accurately. And for that, we need to model the hydrological system. A hydrological model is like a virtual river basin. The model takes dynamic meteorological inputs such as rainfall, temperature, wind speed, humidity, and solar radiation, along with static parameters like soil, vegetation, land use, and elevation. Furthermore, we can incorporate human interventions to make it more realistic at different spatial scales. The model then solves water and energy balance equations, generating outputs such as infiltration, evaporation, and runoff. It ultimately produces stream flow and water level through flow routing. However, to make any model realistic, we need to calibrate it. It means we need to tune its parameter until the simulated variable matches the observed one. And here lies the biggest challenge. We often don't have complete observations, sometimes missing for months or even for years due to equipment failures, maintenance gaps, and data sharing issues, particularly during extreme events, which hinders our ability to calibrate our models. Now, to address these gaps, we have collected data from 343 stations across 15 river basins in peninsular India. We noticed that basins such as Brahmani, Godavari, Krishna, and Narmada have long-term and dense records, whereas Sabarmati, Northeast Coast, East Coast, Pennar exhibits lesser data availability. Moreover, we found that after 2010, the availability of water level data dropped below 40%, and after 2018, stream flow observations nearly vanished from the public databases. To fill these data gaps, we developed a machine learning framework that uses meteorological and geographical features with nearby stations behavior to fill the missing records from 1961 to 2021. Through these continuous data sets, we are not just improving the modeling and prediction, we are reconnecting with the true stories of our rivers. A story essential for a sustainable and water secure future, because water is life and understanding its changing rhythm is its first step toward protecting it.